Thank you very much for the invitation. This talk is based on work done with Justin Corey at University of Pennsylvania. So as you all know, Lambda CDM, in which dark matter is introduced as collisionless massive particles, is in a remarkable agreement with observations. In fact, it fits background expansion history, linear growth of structure, and CMB and matter power spectra amazingly. But when it comes to small scales, in particular galactic scales, the situation is less clear, and there's few challenges that emerge at galactic scales. In particular, the density profile that one finds as a result of n-body simulations takes this more or less universal form, which has two free parameters, ρs and rs. And as you can see, it exhibits the cusp in the center. So as r goes to 0, density goes as 1 over r, which is not what we see when we observe galaxies in our universe. So usually galaxies tend to have more fuzzed out core. Also, in order to explain the observed flat rotation curves of spiral galaxies, one needs to have density go as 1 over r squared, which, as you can see from this profile, it never really happens. So at small r, it goes as 1 over r. At large r, it goes as 1 over r cubed. So in order to explain, of course, it is possible to fit these flat rotation curves within Lambda CDM. One needs to do some kind of tuning so that the distances at which we measure these rotation curves come exactly at the transition, near the transition point from 1 over r behavior to 1 over r cubed. So that's how Lambda CDM can account for flat rotation curves, which may seem a bit unsatisfactory. There are also, related to the density profile, there are also, as you've heard, missing satellites / too big to fail problem, which is basically discrepancy in number of predicted massive satellites for Milky Way and observed ones. So usually simulations seem to predict more massive satellites for Milky Way-like galaxy as compared to the number that we see in observations. But in my opinion, the most puzzling is the so-called Baryonycholoficial Relation. So this plot was borrowed from this paper. So this relation tells us that the baryonic mass in these galaxies is related to the asymptotic circular velocity in this way. And so here, blue dots represent star-dominated galaxy, and the lighter blue ones, the greenish ones, they represent the gas-dominated galaxies. So as you can see, the galaxies in the universe, they follow this rule quite well. So the scatter is very small around this relation, the slope being 4. However, Lambda CDM predicts this relation. So standard collapse theory for collisionless dark matter particles. So, and they predict this relation between virial mass and the virial velocity, which has a slope 3, but it doesn't mean that it is inconsistent, of course, with the Tolly-Fisher relation, because the dictionary between virial parameters and baryonic ones can be mass dependent. So in principle, it is not inconceivable to get this behavior. However, it is puzzling that how can the baryonic feedback processes, which have some level of stochasticity in it, how can they account for such a small scatter around this law? So usually, when people reproduce this relation using simulations, they get significantly large scatter, unless they fine-tune too many parameters in the simulation.
So, this is not very small scatter. It's a factor of 2 or 3. So I'm not sure what you mean by it.
Right, but as compared to what people see on simulations.
I think then the fair thing is to compare it with what people see in simulations.
But especially at high mass,
at high mass, those two are basically parallel to each other. So the two are essentially the same thing. So it's just a constant baryon to sort of mass fraction.
Okay. Yeah, but anyway, I see your point. It is quite possible that once we learn how to do more precise numerical simulations, maybe it is. But so far, there is no indication that simulations, as the precision will improve, will be able to recover.
I think the problem is the simulations as they stand, they're not predictive because you have to. There are so many unknown processes that you have to put in by hand, and essentially, you have to use this type of observations to constrain those parameters. Right. So at that level, you cannot really trust them to give you anything. Okay,
but at this level, then at least there is no real reason to expect there is no we don't really have a good understanding why we should expect in lambda CDM this Baryonycholoficial relation. It's kind of a mystery why it works. Okay, the radical alternative to lambda CDM is to dark matter models is so-called MOND, which stands for Modified Newtonian Dynamics. It was introduced by Milgram in '83. So basically, Milgram's idea was to remove dark matter from the picture altogether and replace it by the modification of gravity. So this is the empirical force law he introduced. So he postulated that the acceleration of a probe particle is Newtonian, like the one we have in GR, for large accelerations. And it is modified for small accelerations in this way, where A0 is a parameter of the theory, and the best fit to observations, it corresponds to A0 of order of Hubble constant today. So good thing. So first of all, this modification of the law, of the force law, it predicts flat rotation curves. It was engineered to give basically flat rotation curves, and it also reproduces Baryonycholoficial relation. It's a direct consequence. However, of course, it fails on cosmological scales. So without significant dark matter component, it's basically impossible to get anything right at large scales. The observation that MOND and CDM, they are so successful at mutually exclusive scales, basically different regimes, has led people to think about some kind of hybrid models. And under hybrid, what we usually mean is that we have dark matter component and plus modified gravity component. So that dark matter will be responsible for getting the large-scale physics right, and the modification of gravity will kick in at galactic scales and give us flat rotation curves and avoid, hopefully, cusp problem and so on. But it's usually the first challenge that one faces when tries to engineer such hybrid models is to arrange for the theory to find a theory that avoids the coexistence of this dark matter and MOND behavior. Because if you start with you have dark matter that acts as dark matter at large scales, then the question is when it collapses at short scales how it behaves. Because if it gives if the contribution at short scales is as strong as in lambda CDM, then both MOND and dark matter may be too much. So usually one ends up introducing some scales in the problem by hand that are of order of kiloparsecs that basically stops dark matter contributing significantly at short scales. So, but it will be much. So here, these models are, as we said, they are based usually at two completely distinct components. So there is no a priori relation between these dark matter components and this modified gravity component. So it will be much more interesting if we could come up with some unified picture. So for instance, if dark matter and MOND regimes, these two components, if they can be different phases of the same underlying substance, then it will be quite interesting. So I'll try to convince you that superfluidity is the way to go to find this unified picture, and I'll try to convince you that these two behaviors can be unified under one umbrella of superfluidity. So first, I'll try to convince you why would somebody will even think about superfluidity. In order to understand why superfluidity may be interesting is to look at MOND theory. So if you can think of this modified MOND force law as a force mediated by the exchange of the scalar field. If you think of this force law this way, then the action for the Lagrangian for the scalar field should take this following form. Okay, so which looks ugly and repulsive, but the fact that superfluids may be interesting.
When you said repulsive, you mean repulsive as a
no, the repulsive is ugliness. Yeah, morally, yeah, yeah. But this repulsive, this repulsive nature of this Lagrangian is actually the indication of why superfluidity can be interesting. So we should compare this to the low energy effective theory of superfluids. So usually, superfluids at low energies, the only relevant degrees of freedom are collective excitations. And so usually in certain class of superfluids, there is always one massless excitation, which is called phonon, whose effective theory is governed by this P of X theory, where X is given by this. So mu is the chemical potential and phi is the phonon field. And P, of course, what function of X we have in the Lagrangian, it is determined by the properties of the superfluid, in particular by equation of state. For a given equation of state, there is fixed P of X behavior. For if you consider, for instance, helium atom condensate, which have 2-to-2 scattering contact interaction, then this P of X. Okay, I don't remember in terms of, yeah, it goes as X squared. So in particular, equation of state is the pressure proportional to rho square, which is the indication that, so since pressure is usually sourced by the interaction, so pressure proportional to rho square, it's a sign that there is a 2-to-2 scattering that sources this pressure. But anyway, so the main message is that this P of X, so this P is determined by the properties of the superfluid. But okay, so we said that okay, so we have this nice observation that these MOND-like actions seem to be emerging in some very special superfluid theories where gradients are strong. But of course, the first question is like fractional powers, right? So can we really have the superfluid with X to the fractional power? The answer is found in the condensed matter literature. So there are unitary Fermi. There are systems which are called unitary Fermi gas, which they are actually the superfluids exactly at the crossover between BEC and BCS. So as you know, so BEC type of condensates are the condensates in which you have strongly bound bosonic degree of freedom, which just undergoes Bose-Einstein condensation, just bosonic degree of freedom going into the condensate. So BCS type of superfluids are different. So then there you have we have fermionic system. So these fermions form some Cooper pair kind of bosonic degrees of freedom, which then condense. But these Cooper pair degrees of freedom are not strongly bound in the sense that these fermions in different Cooper pairs can actually interact with the fermions from other Cooper pair. So this unitary behavior, this unitary Fermi gas corresponds to the superfluid that is actually at the crossover between BEC and BCS. And the way it is achieved on experiment is people tune the magnetic field, and by tuning magnetic field, they tune the scattering lengths of the fermionic atoms, and so this unitary point corresponds to the point when the scattering length diverges, and yeah, people are very excited. So in condensed matter literature, people discuss these systems a lot. So as we see, there are examples in which you have fractional powers in the superfluid action. But still, having one example of superfluid with a fractional power in effective action may not mean anything. So what about x to the 3/2, right? So can you get x to the 3/2? So to say this, let's consider a simple system of massive complex scalar fields that have 3-to-3 interaction as a dominant interaction. So it is easy to see that this system has. So first of all, you would say, okay, can I really have a system with 3-to-3 interactions without 2-to-2 interactions, right? But as it turns out, I mean, of course, I can write down some 2-to-2 interaction, phi to the 4 here, and as long as the coefficient is few orders of magnitude lower than 1, it's not a problem. So phenomenologically, it could still work at for densities that we are interested in galaxies, this phi-4 interaction term could give negligible contribution. But anyway, just to see whether we can get x to the 3/2, let's just consider this theory. It seems reasonable. So of course it has. I mean, you can find that it has Bose-Einstein. It can undergo Bose-Einstein condensation. And in fact, if you compute the effective theory of phonons, you get exactly Lagrangian is exactly x to the 3/2. And the reason is simple because actually, so as we said, the functional form that appears here, it determines what type of superfluid it is. So in this case, x to the 3/2. So we will come to that when we talk about the properties of the superfluid. But x to the 3/2 corresponds to the equation of state p proportional to rho cube, which kind of basically indicates that there is a 3-to-3 interaction that is the dominant interaction.
How can you see that if you start from that top Lagrangian, that gives you p going as rho cube? Is that?
No, so you can see it from here.
But that I can see, but the one up there.
From here, p goes. So p is usually the Lagrangian. So then you have to find what's the functional dependence of L on. First, you get on the chemical potential, which depends on lambda, and the dependence on L on the chemical potential will be mu to the 3/2. And you can see that in this way. So chemical potential comes in as a expectation value of the phase of the complex field usually. So it's a background. So the background solution of phi will be some vacuum expectation value times e to the I nu t. So actually, not quite. So this will be relativistic mu, but then you can write relativistic mu as mass plus non-relativistic mu, right? So as a result, this Lagrangian, once you substitute this background there, you get it depends both on V and on chemical potential. So now V is related. Yeah.
What happens to the phi to the 4th term?
No, here I was ignoring phi to the 4th term.
Why are you ignoring phi to the 4th?
So I'm just considering this as a toy model to see whether
he wants to get x to the 3/2.
x to the 3/2. Yeah.
So you have one where the 3-to-3 is more important than 2-to-2 interactions?
Yes. There are systems where people have studied these kind of interactions, but there they have to tune the 2-to-2 interaction to be small. Yes. But here actually, so the thing is that we need this behavior at densities that are comparable to galactic densities because we want to get MOND-like behavior in galaxies, right? So as a result, you can ask how small this phi to the 4 should be, right? The overall coefficient, how small the coupling should be in order for galaxies that to be negligible. And it boils down that it should be a few orders of magnitude smaller than 1, which does not sound too dramatic for us.
Smaller than 1 compared to the
smaller than 1.
Because the dimensionless coupling.
Yeah, so that one will be dimensionless coupling. This is dimension full. So the point is that this model doesn't really work for our purpose. It's like a toy model, but let's say if it were to work, then this lambda would be some 1 over some energy scale squared.
Yeah,
and that is fixed by, that's milli-electron volt.
Milli-electron volt?
Yes.
What is the mass of phi?
Electron volt around.
So you have an effective operator that subtracts.
So it's a non-relativity, yeah. So if this were the theory, but it this doesn't work. But if it were to work, then you would have just particles whose right. So their description breaks down at energies. So momentum transfers below mass, so that they can be only treated as non-relativistic. Like if you take deuterium, right? Deuterium has a mass which is much higher than the binding energy. So
not sure, but the
yeah.
Lagrangian you're writing down because it has the m squared term, it's relativistic. So it looks like.
No, I know, but this is well, even non-relativistic theories can be written in a relativistic form. That's what I meant. Yeah, yeah. So yeah,
no,
but yeah,
but you
I
have
understand.
an effective
Yes.
operator.
Yeah, yeah, I understand. Yeah, yeah, you're right. But this system,
no, you
yeah,
take it as a toy model.
yeah, it's just a toy model just to see how to get x to the 3/2.
Are you going to talk about the reality? Because you might say, okay, in condensed matter systems, I can buy it. Lots of things can happen.
Yes.
But you might say, cosmologically, look, I'm going to need a potential at cosmological scales that's more or less just dependent on time, and certainly galaxy and smaller scales is basically just spatial dependent. So there's no way there can be something like, oh, at least you might worry that you can't do both, and one of the others of these is going to lead to an imaginary Lagrangian.
For large radians, you mean?
Well, in one regime or the other.
Yeah. So we have more. So this system doesn't work actually for the reasons related to what you just said. I think because actually when if you take this superfluid this theory seriously and you find the superfluid phase, right? So it has the correct-ish looking equation of state, but in order to be able to get this MOND phenomenology out of it, to have to allow presence of strong gradients, you need to have lambda to be negative, which corresponds to the attractive interaction, and which means that superfluid will be unstable. So there will be Jeans instability. So you start with if you form a Bose-Einstein condensate with particles that have attractive interaction, so it's unstable. Then it will break into droplets, and so it will be unstable. We have a better, slightly improved toy model in the sense that it's more complicated, but it allows to have you can compute the backgrounds with strong gradients and study perturbations, and it doesn't have any problems.
To me, that sounds like a different problem, but
yeah.
Let's see what you.
But at this level, yeah. So I just wanted to motivate that it is possible to get this kind of equation of states, because I actually for what I was talking about, all I will be really using is what type of equation of state I have for the superfluid. So most of the discussion will be try to be as independent of the microscopics as possible. But of course, at the end of the day, you need to find microscopic theory to say that here I have the theory of dark matter. But we are not there yet. Yeah, we have a toy model that works better than this toy model, which allows for strong gradients, but it's more doesn't have any illuminating behavior. So doesn't. I can tell you at the end of the talk if you want. But at this level, they just try to become comfortable with the fractional powers in the effective theory for phonons. Okay, so if you became comfortable with fractional powers, then we can ask the more general questions of whether under what circumstances we can have Bose-Einstein condensate in galaxies, right? Because we said that superfluidity can be the way to go to unify dark matter and MOND behavior. So now we have to see under what conditions the dark matter particles that behave like dark matter at the beginning of collapse will start to behave like superfluid and form Bose-Einstein condensate. In order to have Bose-Einstein condensate, as you all know, the particles should become degenerate, which means that the de Broglie wavelength of the particles, let's say if I have a system of n particles, should become bigger than the interparticle separation, right? So that's how the degeneracy happens. So this is very assuming this argument is of course assumes that the interaction between particles is small. So this translates as an upper bound on a mass in terms of density and velocity of the characteristic velocity of particles. And now if we want to apply this to galaxy, we have to. We can apply it at virialization, because that's the time when we can meaningfully talk about halo as an isolated system. So let's apply this relation to Milky Way-like galaxy at virialization. This will translate into the upper bound on the mass of the dark matter particle, which is 2 electron volts basically. So the mass, if we want to have Bose-Einstein condensate in galactic scales, in Milky Way-like galaxy, then the mass of the dark matter particle cannot be bigger than 2 electron volts. Of course, the degeneracy is not sufficient. Like the overlap of wave packets is not sufficient for the formation of Bose-Einstein condensate. Also, we need to make sure that the particles are in equilibrium, and the condition of equilibrium is that the interaction rate should be bigger than the dynamical time for the galaxy. So this, for Milky Way-like galaxy, gives the lower bound on the cross-section. So depending on mass, so this usually we write it as sigma over m should be bigger than this quantity. And for fiducial value that I'll be using throughout we'll be assuming m to be of order of 0.6 eV. The sigma over v is bounded from below by 0.1 centimeter squared over gram. Okay, so of course, so we talked about halo, right? So first the halo virializes, then the characteristic velocity for the particles is set by the virial velocity, and then we checked what are the conditions that need to be satisfied in order for the system to undergo Bose-Einstein condensation. But now, since we know so we know what's the virial velocity of the particles that were undergoing Bose-Einstein condensation, so we can use virial velocity to estimate the effective temperature, right? So because since it was a system of moving particles, it's not really at zero temperature. So one should think of the halo as a condensate at finite temperature, and the temperature, as we said, is related to the virial velocity, and the virial velocity is related to the mass of the halo itself. So we can make this nice plot. So we also know that the number of particles in the condensate, as compared to the total number of particles, it increases with so decreases with increasing temperature, right? The closer you are near the critical point, critical temperature, more particles are excited, right? So actually, only at the zero temperature you have all particles in the system in the ground state, right? So right. So because if you have finite temperature, then you have finite number of particles that are not in the condensate, and actually the relation for if you assume ideal Bose gas, the relation is simple. So number of condensed particles over n, it goes as T over Tc to the 3/2. So exactly T equals to Tc, actually all the particles are actually excited, so none of them are in the ground state. And then once you drop the temperature, number of particles in the ground state starts to increase with decreasing temperature.
So question.
Yeah.
Are there actually solutions to equilibrium solutions for the condensate in, gravitational equilibrium?
Which one?
If you put everything in the condensate, which is happening at low masses.
No, but I'll talk about this, yeah, but
okay.
Yeah.
Because one thing we know is that the constant temperature, there is no constant temperature solution of this gravitational self-found system.
Yes.
Because they're bigger unstable if the size is bigger than something. So it's just gene instability. So, and I don't really know, I would imagine the same would be true for a Bose-Einstein condensate. If you want to put it at constant temperature, then there would be a gene instability that would form.
Well, of course, the particles that are orbiting the center of the halo, right, at different radii will have different velocity, right? So effective temperature is different. But once the temperature at virialization is temperature virialization is below critical temperature, then the core is colder, so it will be even better condensate inside.
But the question is, will it reach equilibrium, or will we just make a colder and colder core, which collapses to basically to a point? So that's
no, actually, we will see that since the cold halo is a superfluid with a given equation of state that we talked about, and we can use the hydrostatic equilibrium to find the profile.
But
it has pressure, so
equilibrium question is stable.
Yes, yeah. I'll talk about stability. Okay. It's actually, stability is more involved than that, especially when we introduce baryons. But without baryons, the halo is stable, and we can check.
What happens in the air?
I'll talk about that. Yeah, that's also an important point. So here, as we see, depending on what mass we'll choose, different objects with different mass can be either completely in the condensate or partially in the condensate and partially excited or completely excited. For instance, if so since we are taking M to be like 0.6 electron volt, so Milky Way, like galaxies, let's take the Milky Way somewhere here. So then it's basically practically up completely in the condensate. While if we take clusters, for instance, clusters are like heavy and they are basically either significantly or completely excited. So superfluid is not a good approximation in clusters because temperature, since virialization velocities are higher in clusters, temperatures are higher. So this framework distinguishes between clusters and, so distinguishes between clusters and galaxies, which is good because we know that MOND is successful in galaxies to recover all these scaling relations, like Untitled relation, but in clusters, it gives you wrong temperature profile, so it's basically inconsistent with the clusters. So, so it's a good thing that we have superfluid only in galaxies. Okay, now cosmology. So first of all, it's a sub-eV mass particle, so it needs to be produced out of equilibrium. It's not a thermal relic. So we are assuming that it is produced through axion-like vacuum displacement mechanism. So imagine this scalar particle to be frozen and the potential displaced from the minimum. So it's sitting there for high energy densities. It becomes dynamical, so scalar field will start to oscillate once the curvature scale drops down to order of mass of the particle. That's when the particle will stop being frozen and start to oscillate and start to behave like a collection of particles. And the temperature, baryonic temperature that corresponds to dark matter particles becoming dynamical is the order of 50 TeV for the mass, for 0.6 eV mass. And you can also, it's very easy to check that very soon after these particles are generated, of course, very soon, since velocity redshifts with a scale factor, they become non-relativistic very soon. And you can check that if you satisfy these condensation properties at galactic scales, you also satisfy them cosmologically. So cosmologically, too, you form superfluid. And and here you can see what's the T over Tc is really small, so it's a very cold superfluid. And just to compare with the Milky Way case, so in Milky Way, T over Tc will be 10 to the minus 2 only. So although Milky Way, halo of the Milky Way will be also significantly in the condensed form, but as compared to that, cosmologically it's a much colder system. And this will be important, so I'll comment on that.
Sorry. So I just wanted to make sure. So the bond we have on cross section, is that consistent with the Miller cluster?
It is for the face, even for the face value, it is because the upper bound is 0.5 from these merging systems. The most recent one.
And the value that you had was what?
Is 0.1.
Was 0.1.
0.1.
How did it depend on the mass?
Yes, for our mass it was 0.1.
Okay.
Yes,
Okay,
yeah. So if I would decrease the mass, the lower bound on cross section would decrease also. But actually, these bullet cluster systems, I'll talk about that. It's an interesting system. So because of the superfluidity, it needs to be considered whether even the bound applies.
Oh, sorry.
Yeah.
If it already condensated at that time, the early time, how does it reproduce large-scale LCDM behavior?
Right. So the point is that I'll talk about that. The thing is that you are in the superfluid, but the equation of state needs to be non-relativistic. It should be much smaller than 1. So pressure should be negligible as compared to rho. I'll talk about that. Yeah. There is a caveat about it. So yeah, that's a good point. Yeah.
It's not in the Bose-Einstein condensate at this point. So presumably it's not in the ground state. Your oscillations of your
So let's say at this point they start to oscillate.
Yeah, but when you're saying what temperature are you saying it becomes superfluid at?
So we basically we just estimated it at equality. At equality, it's already the temperature is this. So it's gonna
matter radiation equality.
Yeah, matter radiation equality. It's already for sure. Yeah, it actually will condense before, but we just made sure that. Because it's important what's happening at equality, right? Before that, it can do whatever you want. Yeah. So at equality, so it's a condensate at equality, and then moreover T over Tc, as a result of further expansion, it's constant, stays constant in matter radiation. In matter-dominated expansion. Yeah. So that's true. So we need to make sure that our superfluid has negligible pressure at equality, which. So again, we said that. So as we said, the superfluid properties are encoded in this effective theory for phonons, and So far, discussion was very general, right? So we said that what do we need? What are the bounds on mass and cross-section in order to have superfluid? And usually there is a literature on vast literature on dark matter Bose-Einstein condensates, right? So where they also want to have condensates in collapse structure, and then they try to explain the flat rotation curves by the density profile of the condensate. So this is where our story differs from their story, because we don't. Because if you try that, it turns out that the system, the constraints, if you combine all the constraints, there are tensions. So it's hard to satisfy constraints coming from getting flat rotation curves and also satisfying the bullet cluster bounds. So the story in our case is different because we do not use the profile itself to generate flat rotation curves. Instead, we want these phonon fields to act as a MOND mediator, so mediator of the MOND force. So motivated by the success of MOND at the galactic scales, we just conjecture that the equation of state will have this x to the 3½ behavior. So let's assume that that's the case. Moreover, in order to mediate the force, these phonons need to couple to sources, right, to baryons. So this coupling that suffices is this phi baryon coupling, which is, of course, it breaks the shift symmetry of this action, but it's a very soft breaking because it's suppressed by M Planck. So if you try to estimate whether you will generate the mass of this phonon because of this interaction, you will find that it's much smaller than the Hubble scale. So this coupling is innocuous from the point of view of radiative corrections.
So what is lambda?
Lambda is a parameter of the theory.
Okay.
Okay, so as we said,
what is the dimension of this? Because low baryon is dimension 4.
Is dimension 4?
Phi is dimension 1. So
No,
dimension 5.
phi is the dimensionless actually in this case. So it's misleading. Yeah.
Okay.
Yeah, sorry. Yeah.
Yeah.
So this is phi dot and yeah.
Okay.
So canonical normalization would approximately account for removal of lambda actually from here if I were to normalize canonically. Approximately, not exactly, but. So given the effective theory for phonons, we know what's the equation of state. As we said, we just set phonon fields to 0, and we get, and since Lagrangian basically tells us what's the pressure, we get the pressure as a function of the chemical potential, which we can use like using standard thermodynamic relations to find the number density, and at the end combine everything and get the pressure as a function of rho. So in our superfluid, the equation of state will be behaving like this. And also you can study the perturbations around the superfluid, and you will find that actually perturbations are stable, and the speed of sound for the perturbations is given by this relation.
That wasn't the kind of stability I was talking about.
That's not the stability you're talking about?
I was talking about Jeans' stability, not the...
Yes, but so Jeans...
that involves...
Oh yeah, if you start... Okay, yeah, okay. So that we will come to that. I mean, we can use. I mean, the point is that given this equation of state, we can find out what's the profile, right, as a result of equilibrium. And what we find is that the density profile will be chord. So it has this cosine behavior. So hence we don't have the cusp problem here. And for fiducial values, which are m is 0.6 electron volts and lambda is 0.2 milli electron volts. Actually, that works the best for phenomenology, and also to get right sizes. So Milky Way-like galaxy, we get the radius of the core of the superfluid core to be around 125 kiloparsecs. So within this distance, with a good approximation, you just have a superfluid basically with that profile. Of course, outside of this superfluid core, there will be some envelope of dark matter particles in the normal phase, which most likely will be like the tail of NFW density profile. But
sorry, at this point I'm confused about what happened in a galaxy. Is that you have this dark matter component not only giving you extra mass, but also mediating extra force.
Yes, that's right. So
you combine both effects.
Yeah, you have to combine. But the thing is that the gravitational effect of halo, because you have a halo, so it also creates gravitational potential, right? Because it's now cored, actually, it will end up to give you negligible contribution for the distances that you care for flat rotation curves. So anyway, we check it explicitly. Huh?
And so you have some predicted scale of which flat rotation curve should turn over and begin to fall off.
Yes, yeah, we will have that. Actually, it will be around 70 kiloparsecs because that's exactly the point that was just raised. So you have this halo and you mediate this MOND force by exchange of phi, but you also have gravitational force of this guy, and you can ask the question. So the size of this core is 125, the whole size. So the question is how far you can go without and still be able to drop the gravitational effect of the condensate itself, and that's around 70 kiloparsecs. Yeah, and the flat rotation curves are observed from like 10 kiloparsec to 50 range usually, so it's fine.
So if we put in there like a dwarf galaxy mass, what numbers do we get?
Okay, I don't remember on top of my head, but there is a mass dependence of R on.
But will it give you about the right radius of dwarf galaxies?
So I think it does give you for those for the size of galaxies for which you have this rotation curves, it gives you right size because it's so this R depends on the mass, but it's a mild mass dependence. So it's a fractional power of so R depends of course on the mass of the halo, but it's a fraction. Dependence is a fractional power, so it's a very mild dependence. So you still so anyway, the answer is that yes, even for small galaxies,
you like, like the satellites in the Milky Way, dwarf galaxies there, where we have evidence for dark matter on a fairly small, on a like less than on a kiloparsec kind of scale. Does it give the right clustering properties for those?
I think so. Yeah.
So. Oh, so actually no, there it won't be superfluid. There will be.
I think, yeah, as long as you have the same fraction. If you have dark matter, yes, you will get, yeah.
How does the density perturbations evolve? What is the gene scale? I mean, this is.
No. I'll talk about it. So we have to. So of course, you have to make sure that this equation of state is non-relativistic, right? When structure forms in the linear regime, right? Yes. So yes, that will actually will force us to introduce some temperature dependence of these parameters. Anyway, so I will comment about it.
On what?
Just remind. I mean, okay. I'll come. I think I'll come to that. But okay, the answer is that I think even as I recall, even for dwarf galaxies, you also get. I don't remember exact number of what's this size.
The point is there, we need the dark matter distribution to be sort of a lot smaller and denser than this 125 kiloparsec. Okay,
it will be, yes. Yes. No, but it will be smaller because this relation depends on the mass. But yeah. I just don't remember numbers off the top of my head. But because when we got the relation and we checked all the relevant numbers, nothing was absolutely terribly off about it. Okay, so because of the core, because of having a cored core of the halo, it's of course there is no cusp core problem, and also it avoids the too big to fail problem, which I think I did not mention, but it's basically because I think I did. It's basically anyway, this discrepancy between predicted and bright large satellites for Milky Way and observed ones. So these two numbers.
So just presumably the point is in dwarf galaxies, the dark matter density is going to be higher. It's not in the superfluid phase anymore. Is that the idea?
Actually, no. As mass decreases, you are actually superfluid is a better approximation because as we saw from that plot. Because it also determines the temperature, right? So mass also determines what's the virial velocity. So effectively, it determines the temperature also. So smaller is the mass, better is the superfluid approximation.
Okay, but not, so not about the ground state of a Bose-Einstein condensate, but about some other state. Is that it? Okay, I'm a bit confused by that. Oh, maybe I'll say it.
Yeah, but we can chat later. Yeah. Okay, so all right, so we have this nice, more or less homogeneous core of the superfluid, and we can study. We can find the force mediated by these phi fields, the phonons, in the regime when gradients dominate and when we are in the MOND regime. And then, so the acceleration for the probe particle will be given by this expression, and so I just wrote this to relate the parameters of our model to the A0, which was the parameter of the Milgram's modification of gravity. So basically, so A0, the best fit was of order of H0. So alpha, if you consider it to be of order of 1, that's actually the best fit corresponds to lambda to be of order of milli-eV, basically. So we can plot the acceleration as a function of r. So here we compare a phi, which is the solid line, is the force in our model, and the dashed line is the MOND force, which is basically, you see that they basically match. And this is the ratio of these two forces. And of course, here, so far we have not included the gravitational effect of the halo. Now, if we introduce the gravitational effect of the halo, what we find is that that force becomes relevant only at scales of order of 70 kiloparsecs. So you have this nice range from around few kiloparsecs to 70 kiloparsecs, in which in this distance range you recover MOND phenomenology.
So would lensing be very different?
Yeah, so with lensing, so usually with the MOND, since you don't have dark matter at all, you need to have these Teves kind of models in which you introduce some not only conformal coupling to matter, but you introduce a vector field that you need to write this very special coupling. So in our case, I think since we have some dark matter, right? So we have more freedom in how we couple to baryons. But in principle, we may also need to have some kind of non-minimal coupling of phi of this. So phi times rho baryons, this coupling may not be sufficient. We may need to generalize that coupling. I have a slide for that if I have time. I'll
So when you see these talks by Stacy McGaugh about fitting MOND to data, one of the things he always shows these plots that emphasize that it seems that if you want to modify the force law, that it's modified not at a characteristic length scale, but a characteristic acceleration scale.
Yes.
Is that what's the story?
Oh no, I think no, it will be the same. Here I was giving the example of Milky Way as an example. Right. But of course, in reality, it will depend on because if you have a halo that's not even 70 kiloparsecs, yeah, then.
Yeah. Is that maybe that's it? Is there a simple characterization in this approach? Do you end up reproducing essentially that prediction that the modification from Newtonian gravity happens?
So here it's not so simple because we have this dark matter, and I think best we can do is to just check that gravitational effects of the halo was negligible. I think because I mean in a MOND case there is no halo to begin with. Yes.
Is there a non-Lagrange degree of freedom that mediates this force? Why 70 kiloparsecs? So what is the phonon mass? So there's a phonon, you say mediates.
It's a massless particle.
Okay. So
but
why doesn't violate the equivalence principle if you add coupling to baryons by hand, the scalar coupling to baryons?
Right. So the point is that actually, yeah. So when it comes to, for instance, like solar system tests and so on, in principle, actually, I have a slide for that too, which probably I won't be able to show. But so usually this MOND, although it is a small correction to the Newtonian force in the solar system, but it's still a significant contribution. So it contradicts. So usually one needs to invoke some kind of screening mechanism, additional screening mechanism to complicate the theory. In our case, the situation is a bit simpler because one can argue that so near stars, the gradients are so strong that the superfluid description breaks down. Actually, so within solar system, so of course we have the.
What do you mean gradients are strong? The
So
from the sun is
no, the phi force, right? The force mediated by phi, the phonons, is too strong. So for example, the condition that we checked was that so you can associate the velocity to the superfluid that is usually you can estimate it as the gradient of the phase divided by mass. So you can check whether this velocity is smaller than the critical velocity of the condensate, and that gives you the lower bound on the distance from the center. So if you want to have V superfluid to be much smaller than the critical velocity at which superfluidity happens, it gives you lower bound on distance from the center. So if you get too close to the source, to the baryonic source, actually you violate this relation. So you would expect.
So then why don't stars break down superfluid in this?
Yeah. So what happens is that so you have so of course you start with a halo, which is superfluid. Then when you have local sources in the vicinity of the stars, you will have the breakdown of the superfluidity, and the dark matter will be in a normal dark matter picture. While away from the stars, it will be more into will be in the superfluid.
When you say away, how far away?
Far away.
How far?
How far?
So for sun, for instance, it's around for our masses, it's like 250 astronomical units. So it's larger than the size of the solar system.
That's convenient.
No, this was just a check because we were trying to see because the thing is that we create strong gradients for this phonon field. So at some point we expect it to break down because what we had in mind is that since this P of X theory is just a leading term in the derivative expansion, right? So there are some corrections, and in principle, like we have experience with these Galilean models and so on, we could use those high derivative interactions to screen this force. And that was, I think, proposed as a screening mechanism by Defayed and Babichev. Yeah. So even in MOND, what people do, since they don't have the superfluid picture and they have modified gravity all the way or all scales, they need to introduce some screening mechanism, and one can do with this Weinstein screening. Okay, so the force law, we said it's very similar to MOND, but actually, when you study perturbations around this force law, you find that there are instabilities actually. So if you were to take this halo with baryons, so without baryons there was no instability, but with baryons, if you take this zero temperature theory for the phase value, you find instabilities. So, but as we said, so the galactic halos are at finite temperature, right? So T over Tc was 10 to the minus 2. So one can in principle argue that the finite temperature effects can help to stabilize halo that would be otherwise unstable. And you can within effective descriptions of these fluids, you can actually show that it is possible to have low energy effective theory for finite temperature superfluid for which you don't have this instability. But again, so this needs to be checked, of course, once we find precise microscopic model. Okay, this was actually this comment about the breakdown. So this is the R, this bound that. So for Milky Way, you get this bound that you can. R needs to be greater than this, which is the okay bound. And then if you apply this to Sun, you get that superfluid description is valid at large distances. Okay, now cosmology, right? So we said that we have this equation of state, and of course at low densities, this is basically sound speed is 0, right? And so it seems fine, but we need to make sure that it's a non-relativistic, it says dust-like equation of state all the way to equality. That actually gives us the lower bound on lambda, and we get lambda to be, should be bigger than 0.5 electron volts. And if you compare it to the lambda that we get at galactic scales, it's actually 4 orders of magnitude bigger. So here, but however, we can recall that the temperatures were dramatically different at galactic and cosmological scales, right? So there's more than 20 orders of magnitude difference. And since this lambda was a parameter of the effective theory, there is no reason to expect it to be independent of the temperature. So of course, we don't have any real justifications why, I mean, what kind of temperature dependence, I mean, we don't know what kind of temperature dependence this effective parameter should have, but at least it doesn't sound unreasonable for these parameters to change by 4 orders of magnitude or more if the temperature difference is more than 20 orders of magnitude difference. So there is no reason to expect these parameters to be the same. But of course, without explicit model, it's hard to judge. So yeah, so if we take lambda to be big enough, then it will behave like a dust, basically. So it's a perfect fluid with dust-like equation of state. So
the expected direction of the change is logarithmic.
Yeah, we don't know. I think it will also depend.
By the way, do you have a control of it? Because you expand in part of 1 over lambda of the effective potential. What is lambda? Lambda is a normalization scale, right? And that's whatever effective potential you write down.
Yeah, so that.
So do you have control in the expansion? Because the value of phi field in the galaxy is pretty high. Capital lambda.
No, actually, so you are saying, if I recall, so I wrote pi to the 6 with 1 over lambda squared.
Yeah, and then
I had pi to the 4. Okay, yeah.
And then there's pi to the 8.
Actually, the thing is that pi to the 8. This guy, let's say we suppress it with the same to the 4, and then let's find some coupling here.
Yeah.
So as long as this is the hardest to get rid of, because of course the densities are high, but the way it plays out is that this is the most dangerous term. So you have to argue that lambda is a few orders of magnitude below 1, but g needs to be just somewhat below. If it's smaller than 1, then it's fine. But of course.
How big is phi, actually? This is the phi there.
Phi. So it depends. It really depends on what's the particular model we consider. The model that I wrote, it doesn't work, but let's take it. Let's say if it works, right?
Sorry, because I'm confused. What phi is the photon field?
No, this is the. Sorry.
This is the field itself.
This is the field itself.
Okay.
And actually for.
So can't you estimate what phi is from the?
Yeah, you can take the you can estimate, and what you find is that g doesn't need to be many orders of magnitude smaller than 1. It needs to be like order of magnitude smaller. So you can estimate it because we know what's the relation between phi square.
Phi squared is rho over mass squared, right?
Phi square. No, but it's more tricky because we have a phonon background, so we have to actually take into account the phonon background. So it's important.
So the self-interaction.
Yeah. So it's actually, it boils down to, it's proportional to lambda. Actually, when you solve equation of motions, lambda comes with some power here, and we also have x to the 1/2 if I can recall. But this x was this mu plus gradient squared and so on. So this phi square depends on lambda also.
To get the right relative abundance, you're estimating
No,
right? So, but that means here, because they have another contribution from kinetic energy, from pressure. Because
you were asking about galaxies, right?
Yeah, I'm asking about the galaxies.
Yeah, though this I checked because the point is that but let's put it this way. So the reason. The fact that I ended up lambda being much smaller than 1 is because the enhancement factor phi 6 to the lambda square is small.
Yeah.
So as a result, these higher order guys are easily satisfied.
Another question, though, that has to do here in the universe. Even without the G scale, you assume that you have a harmonic potential, but the m squared phi squared term is the dominant one when the field starts oscillating. scale.
Right.
So if you go to the early universe where the field started oscillating, the amplitude was much higher. So it's not obvious the potential will behave as a
yeah, so it could be. Yeah, we took very simplistic approach. Yeah, we just took the mass to be the dominant. What I said about cosmology was assuming that mass is the potential that we need to. But it may change. Yes,
right?
yes, yeah.
I mean, if you also look at the gene scale that you calculated, it's clearly not that lambda that you have there.
Yeah, so you could produce it earlier, but I don't think.
It affects the evolution a lot, right? Because that means the potential that you write down is not harmonic. It's not m squared pi squared, so it won't start oscillating the way you expect it to.
Right,
But it goes along the lines of the gene stability scale.
Yeah, but we just, I mean, yeah, but we assume that the potential is such that the part it has a local minimum around 0.
Yes, but you're not at that scale because lambda you assume is very high.
I know, I understand, but yeah.
Yes, from 1 EV, I mean,
right. So so it could develop additional local metastable minima, and it gets stuck in some. Right. So yeah, I agree. So without full story, there is not much we can say. But we don't even. Yes. Anyway, so.
So how do you know that?
Maybe I
right, but it's a kind of So one step at a time. One step at a time, right? So we just. We are trying to improve on all those questions that you are raising, and which need to be addressed. But again, it will highly depend on what's the particular model that we are considering. And it's not. First of all, it's nowhere near the simple model that I wrote. It's so the only candidate that one can hand-wavily argue that it may potentially work is more complicated. So we have much less control over it, and I mean. We believe there are some other possible microscopic models that we are missing completely by our simplistic approach that we consider some bosonic degree of freedom that undergoes Bose-Einstein condensation. It could be some BCS type. But sorry, I'll just fast forward. So merging clusters are interesting because these cluster superfluids were at a finite temperature. So you have superfluid. So you have a fraction of the mass in the superfluid phase, and the rest of the mass is in excited phase. So effective phenomenological description would be some two-fluid picture, so mixture of two superfluid and normal dark matter-like particles. So it may have interesting consequences. You may be, for certain clusters, you may be able to even generate these train wreck kind of merging systems in which you have collision of two galaxies, but instead of generating only two mass peaks for just two dark matter halos, you generate more because I mean, there are examples of that. So the consequence, so there will be vortices, which estimated they have small energy densities. There will be lots. So from simulations, we know that at realization, what is roughly the it has some angular velocity, right? So we can estimate whether that angular velocity is above the critical velocity. You will expect formation of lots of vortices in the halo. But unfortunately, the energy density in these vortices are very negligible. It's tiny, so it may be hard to see. It has interesting consequences for galaxy mergers. Because since galaxies are mainly in the superfluid phase, depending on whether inflow velocity is subsonic or supersonic, the superfluid cores will either just pass through each other without dynamical friction, because superfluids at subsonic velocities have no dynamical friction, or if it's supersonic, then it will be more like CDM-like merger. So in one case, there will be multiple encounters because you don't have dynamical friction, while in the supersonic collisions, it will be rapid merger, like in Lambda CDM. So globular clusters are usually problematic for MOND because globular clusters are consistent with only Newtonian force, and we know that it doesn't have that much dark matter in it. The point is that in our case, since we are not exactly MOND, we need dark matter to have Mondian behavior. So in globular clusters, we do not expect to have MOND force law, because there is no enough dark matter to create the superfluid profile. And also, one way to rule out this scenario is the ellipticity of halos. So if, for instance, if you can probe the ellipticity of galactic halos down to small scales like 100 kiloparsecs, then, so in our case, the superfluid core, which was of order for Milky Way-like galaxy around 100 kiloparsecs, it will be super spherical because it has surface tension, and so superfluid core will be spherical. There will be an envelope outside, of course, that will give some ellipticity, but so the question is what scales, at what distances we will measure ellipticity of the dark matter halo. So it may be interesting. Okay, I'll stop here.
So we're after 12, so I would suggest, unless there is another urgent question, maybe we can just go for lunch and ask Lasha any more questions there. Yeah, let's go for lunch.